In this video, we're going to be talking about error analysis. Error. What is error? Error is the deviation of the obtained value from the actual value. Now, it does not include mistakes, and error is never negative. So, absolute error is given by actual value minus the obtained value. So, even if the obtained value is larger than the actual value, we cannot get an absolute error that is negative. Okay, so for example, let's say the height of a boy was measured to be 5 meters, but actually the boy is 5.5 meters. The absolute error will be given by the actual value minus the obtained value, that is the measured value. So the error in this case will be 5.5 minus 5, which will give us 0.5, and that's our absolute error. Now the percentage error will be the absolute error all over the actual value. So what is the absolute error? The absolute error is 0.5 all over the actual value, which is 5.5. That's the actual height of the boy, but we measured it as 5 meters, so we made a slight error of 0.5, and so the percentage error is going to be 0.5 all over the actual value times 100, and whatever we get here is our answer. So I actually got 9.09%, or we could just say 9.1%, and that's our percentage error for that case. That's a relatively easy case. Now I want to note something, because when we start dealing with instruments, the greatest possible error is half the smallest division of the scale. This is known as the estimated uncertainty of a measuring device. Remember when we treated meter rule, and we said meter rule had an accuracy of, can measure up to an accuracy of 1 millimeter. That's actually the smallest division on its scale. Then for vernier caliper, we said it could measure up to 0.1 millimeters. This is the smallest division on its scale. And for micrometer screw gauge, which is the most accurate length measuring device, it has an accuracy of 0.01 millimeters, and hence the smallest division on its scale. Now if they ask you a question in JAMB, the greatest possible error which a meter rule can have, the answer is going to be half of its accuracy. So 1 millimeter divided by 2, the answer is going to be 0.5 millimeters. So this means the estimated uncertainty of a meter rule is 0.5 millimeter. Now for a vernier caliper, we do the same thing. We take half the smallest division, so half of the accuracy of a vernier caliper is also going to give us its estimated uncertainty. So it's 0.05 millimeter, and for micrometer screw gauge, estimated uncertainty is going to be what, 0.005 millimeter. That's how accurate these measuring devices are, with micrometer screw gauge being the most accurate. You can see how small the error is, the greatest possible error. Okay, so in the previous example, we just talked about the height of a boy. We just talked about one dimension. Now what if we're given, let's say, the dimension of a 2D shape, a rectangular plot of land with its width 7.5 inches and its area and its height, or its length rather, its length as 3.5 inches, and they say that the area of this plot of land was measured to be 26 inches square. Now they're asking you to calculate the error, or the percentage error rather. So how do we go about calculating the percentage error? If this was our obtained value, this is our obtained value, that is what we measured, but the actual area of this plot of land is going to be given by the formula length times breadth, right? Area of a rectangle. So we have 7.5 inches times 3.5 inches. The actual area is 26.25 inches squared, but we measure it as 26 inches, so there's an error. What is the absolute error here? We have to subtract it from the actual value, and that's going to give us 0.25 as our absolute error. So the percentage error is going to be the absolute error all over the actual value times 100, which means percentage error is 0.5 divided by 26.25 times 100, and that's going to give us, wow, that's a very small error. That's actually going to give us 0.95% as our percentage error. Okay, so that was just a casual example. Now let's get into a more complex case where we talk about thickness and other quantities. So let's take these questions one by one. So we're going to tackle this first question. A student measures the internal and external diameters of a cylinder as 50 plus or minus 2 millimeter and 60 plus or minus 2 millimeter respectively. The highest possible error in determining the thickness of the cylinder is, okay, so I want us to follow a step sequence. First thing we need to do is to identify what is the main formula. We need to establish what is the main formula, because when we solved this case, we made use of the main formula length times breadth when we're dealing with area of the plot of land. So in this case as well, we are dealing with we're dealing with thickness of the cylinder. So we need to know what the formula for thickness is. So to calculate the thickness of a cylinder, how thick it is, we have to subtract the external diameter from its internal diameter. And to do this, as you can see, there is a range plus or minus 2 millimeters, and we have to get the values for each of this range. So that's what we call what's the tolerance interval. So we have to first calculate what the tolerance interval is for both readings, for internal diameter and external diameter. So tolerance interval for, let's start with the external diameter is going to be given by I'm just underline. So it's going to be given by, this is internal and this is for external. Remember they said respectively. So 60 plus or minus 2 millimeter is for external, which means that the tolerance interval is either going to be 60 minus 2 or 60 plus 2. So 60 plus 2 is 62 millimeters. So 60 minus 2 is 58 millimeters. Now, what do we have to find next? We have to find the tolerance interval for the internal diameter. So we're going to do the same thing. Tolerance interval for internal diameter. Okay, so just like we did the first, 50 minus 2 and 50 plus 2. So we're going to have 52 millimeters to 48 millimeters. That's the tolerance and that's the tolerance interval for the internal diameter. Now that we have both tolerance intervals, we need to find the upper limit and the lower limit. Now, to get the upper limit, we have to subtract the largest diameter value from the smallest diameter value, and that's going to give us the upper limit. Okay, so 62 millimeters, right, is our largest, minus the smallest, which is 48 millimeters, gives us our upper limit, and this is equals to 14 millimeters. Now for the lower limit, we need to subtract the remaining two values that are left. Okay, so we need to subtract 58 millimeters from 52 millimeters. That's what I'm going to do here. So 58 minus 52 millimeters, this is going to give us 6 millimeters. Now some of you may be wondering, why did we even start to subtract in the first place? It is because of the main formula. Let us remember that thickness of a tube or a pipe is equals to the external minus the internal diameters. And that's exactly what we're doing, subtracting the external from the internal diameter to get the upper limit and the lower limit respectively. So the next thing we're going to do is find the greatest possible error, right? Because that's what they asked us to look for, the greatest possible error. And how do we find greatest possible error? Remember this statement here, that the greatest possible error is half the smallest division of the scale. That's the same concept we're going to apply here. So we are going to add the upper limit to the lower limit and then divide it by 2. Take half of that value. So 14 plus 6 all over 2 will give us 10 millimeters. So if we actually check very well, we just need to check this value very well. We can see that this greatest possible error is actually plus or minus 4 millimeters. How do I know this? If you add 4 to 10 millimeters, we are going to get 14 millimeters, which is our upper limit. And if you subtract 4 millimeters from 10 millimeters, we're going to get our lower limit, which is 6 millimeters. And therefore, the greatest possible error in determining the thickness of the cylinder is plus or minus 4 millimeters. I hope it's clear enough. So let's take another example to make sure you understand what we're doing here. Okay, so take this question. The external and internal diameters of a tube are measured with calipers as 32 plus or minus 2 millimeters and 21 plus or minus 2 millimeters respectively. Determine the percentage error in the thickness of the tube. So in this question, we determined the highest possible error. We didn't look for percentage error. But in this question, we're being asked to look for the percentage error. To find the percentage error, we have to look for the absolute error, right? That's the greatest possible error. So how do we go about that? First thing I want you to think about is, what is the main formula for this problem? We are talking about thickness, right? So we're still going to use the same format of external diameter minus internal diameter as our previous question. Okay, so the first step is actually finding the tolerance interval. So tolerance interval for the external diameter, we're going to find that first, and then followed by the tolerance interval for the internal diameter. So for the external diameter, we can see that this corresponds to this respectively. So, and the external has to be larger than the internal diameter. So we can just know, because 32 is way larger than 21. This is definitely the external diameter. So 32 plus or minus 2. So 32 plus 2 is 34. So we have 34 millimeters to 32 minus 2 millimeters is 30, and that's the tolerance interval for the external diameter. Now that's for the internal diameter. The internal diameter. Thirty 21 minus 2 and 21 plus 2, that's going to give us 23 millimeters and to 19 millimeters. That's the tolerance interval for the internal. What's the next step? Upper limit and lower limit. So for the upper limit, all we have to do is subtract the largest value from the smallest value. So the largest, the external diameter, 34 millimeters, from the smallest value for the internal diameter is what to make up our upper limit. So 34 minus 19 is going to give us 15 millimeters. And then for the lower limit, we take the remaining values that are left. Remember, we already used this and this. So next we're going to subtract 30 millimeters from 23 millimeters. So 30 minus 23 is going to give us 7 millimeters, if I'm not mistaken. Okay, so now that we've found the upper limit and the lower limit, what do we do next? We have to add them together and divide by 2 to find the greatest possible error, right? Okay, so let's get onto it. So that means we have to say 15 plus 7 over 2 to find the greatest possible error. So 15 plus 7 is 22. So 22 divided by 2 is 11 millimeters. Now that I've gotten 11 millimeters, the error, actually, this is the actual value. So the error deviation, plus or minus what value we give 7 millimeter and 15 millimeter when you add and subtract respectively. So when you subtract 4, when you subtract 4 millimeters, you get 7 millimeters, and when you add 4 millimeters, you get 15 millimeters. So our error for this case is plus or minus 4 millimeters. And remember that we are asked to find the percentage error. So percentage error is going to be the absolute error, which I've gotten as 4, all over the actual value, which is 11 millimeter times 100%. So if I punch that in my calculator, I'm going to get 36.4%, and that's our percentage error in thickness of the tube. Now, before we move on to the other example, there's something you must note. See this value here. For the last 2 examples we've done, they were the same, but it is not abnormal for them to be different. So whenever you see that the values are different, there is no issue at all. You just use the same principle. So let's take, for example, if this were to be 3 instead of 2. Let's take, for example, if this was 3 instead of 2. Getting the tolerance interval for the internal diameter is just going to be like 21 minus 3 is what? 21 minus 3 is going to be 18. So we have 18 millimeter to what? 21 plus 3, so to 24 millimeter. And we want to subtract upper limit from lower limit. Is going to be the largest from external diameter to this, subtract from the smallest in internal diameter, and every other process is just the same. So I just wanted to point out that it's not uncommon to have different error values. So let's deal with the last case. This will be the last example for this video, and in the group chat I'm going to give you some problems to work on. So for this case, I want us to orient our mind. Even before they read the question, you just need to know that you should look out for what the main formula for that question is. So you have to keep a lookout when you read the question. An engineer measured the internal diameter. Okay, we're still talking about diameters here, of a small pipe with vernier calipers and recorded 4.38 cm instead of 4.35. We can already spot an error here. Calculate the percentage error in the cross-sectional area of the pipe. Okay, so they are looking for the percentage error, not for the diameter. It's not percentage error of diameter, but percentage error of what? Percentage error in the cross-sectional area of the pipe. Now let's bring our mind to main formula. Since they're talking about a pipe and its cross-sectional area, a pipe is a cylinder, an elongated cylinder. So definitely the cross-sectional area is going to be that of a circle, right? And the area of a circle is given by pi r square. This is the area, the cross-sectional area of this pipe. So we have identified the main formula. Now let's find the error in this cross-sectional area. Okay, so with this formula, but in our question we were given the diameter, not the radius, as we can see on this formula. So remember that radius is equals to diameter over 2. So we can transform this formula into that for diameter. So we are going to have diameter square over 4, and this is the new main formula. Now moving forward, let us find the error, the absolute error in the cross-sectional area of the pipe. So using our values for diameter, we just need to substitute and take the difference. So let's go. So to calculate the error, we take our actual value. So we recorded this instead of this. Our actual value pi all over 4 is a constant, right? In bracket 4.35, which is our diameter squared, subtract it from pi all over 4, then 4.38 squared. So simplify further. Since this is the same, it means they are like terms, which means we can just take the square of 4.38 and the square of 4.35 and subtract them. So the square of 4.38 is 19.1844 minus 4.35 squared. 4.35 square is going to give us 18.9225. The reason I'm using up to 4 decimal place is so we get an extremely accurate answer. But in JAMB, you can approximate to 2 decimal places and you still get your correct answer, because the options will not be so close that you can't distinguish what the correct answer is. So subtracting this, I get 0.2619. And remember the like term, pi over 4. So we're just going to bring it here, and this is our error. Now to calculate our percentage error, so percentage error is going to be equal to, remember, the error, that is the absolute error, all over the actual value. So let's go. The error which we have here, we're going to use it 0.2619 pi over 4 all over the actual value. What is the actual value? This is the actual value. How do I know that that's the actual value? I know this because they said we recorded 4.38 cm instead of 4.35. That means 4.35 is the actual value for the diameter, and therefore the actual value for the area is going to be 18.9225. So I'm going to put 18.9225 at the denominator, and so if you bring in the like term, it's just going to cancel out, and we didn't really need it to start with. So times 100. Okay, I think I forgot to put times 100 here because in percentage. So if we divide it now, 0.2619 divided by 18.9225 times 100, we're going to get a percentage error of 1.3%. 1.38, sorry, 1.384%. And that's the end of this video. Now if you gained value, ensure you hit the subscribe button, because we're going to be posting more instructional videos like this. in the future and you want to be the first to know about them.